Welcome back. I hope you had a good break, that it was an opportunity to rest your brain a bit, digest what you've learned in the first hour. So now I will continue on these nines. You know, there's nines all over the place on that slide, and I need to explain what this is all about. This here is a durability guarantee by Amazon, by AWS. It's a guarantee that if you store, imagine, probably you as a user won't have that many objects, but a potential customer who stores 100 billion objects on S3 can expect to lose at most one of these 100 billion a year on S3. All right, so this is a loss. There is no perfect system. You can never guarantee 100%. You know, things happen, hardware gets old, and so on and so on. But you can try to increase that number, and typically it's expressed in terms of nines. You just add more nines if you want more guarantees. Here's another example. This time, it's about availability. Saying that you have 99.99% of availability means that 99.99% of the time, you are not down. This means at most 1 hour. If you compute 0.01% of a year, that is actually an hour, roughly. So the beautiful world of service level agreements, this is what SLA means, is full of nines, and this is how you recognize them. It's lawyer's language. These are the guarantees you give to your customer in terms of the services you provide. This is here just a summary. You can actually compute it very easily if you want, but 99% means that you're down 4 days a year, all the way to 99.99999. I think there's 5 of them, 4 seconds per year. 4 seconds per year is amazing in terms of guarantee, right? And the more you pay, the more nines you get, right? Another example is the response time. The response time is tricky because you could think, okay, you guarantee an average response time, but that doesn't work. What you need to guarantee is a percentile of the requests that are below a certain threshold. So what you guarantee, for example, if you say, okay, I'm guaranteeing 10 milliseconds, that's actually, you won't get that for object storage. For object storage, it's more like 100 to 200 milliseconds. But for the key value stores that we'll look at tomorrow, you guarantee in 99.9% of the case a response time of less than 10 milliseconds. This is the way it's done. You don't use the average or the median. You use some percentile with plenty of nines for which you are below a certain threshold. This is the way it's done. All right. Before that, I need to say a few words as well, because I'm pretty sure that for most of you, it's not a surprise, but for some of you, saying that Amazon provides a service for storing data in the cloud, maybe your reaction was, what is Amazon doing? This is a bookshop, right? You buy books on Amazon. So why are why are they providing cloud storage? Well, it's an interesting story. The idea is that when you are a store online and you need to be available to people, you need plenty of servers. You need redundant server because you have many requests for all over the world. You might also know that depending on the country in which you are, there are going to be moments of the year in which you have a peak of connections. In the US, for example, Black Friday is an example where everybody suddenly connects to get the good deals, right? So in every country, the peaks might be at different places. But if you are a company on your own and you rely on your own hardware, you basically need to buy physical equipment that covers the peak of the year. But the problem is the rest of the year, you just have machines that are not used. And that's a waste. So the idea, the brilliant idea that they had is when we don't actually use our machines for the rest of the year, why don't we rent them to whoever wants to use them? And this is how AWS, Amazon Web Services, saw the light of the day. So they came up then, it became a full service that is actually profitable, where you can rent space, you can rent machines, literally machines. We will see plenty of that in the lecture and so on. And then competitors arrive. So Azure, the Microsoft version, Google Cloud Storage, so plenty of other providers provided the same services, right? The cloud is super important for elasticity. As we will see also during the lecture, because we'll see in probably beginning of December, we'll play with the Azure cluster. Each one of you will just trigger a lot of machines just for yourself in the Azure cloud for a few hours and then query massive quantities of data. This is the elasticity of the cloud. Rather than paying for a single machine for the whole year, you pay for 10 enormous machines for just a few hours. And that's going to be something like $100. But you are not going to pay the $100. This is sponsorship, of course, so you'll get it. But just to give you the idea that the fact that you can get an enormous number of machines for a few hours for a 2-digit number of dollars, this is the elasticity of the cloud, right? You just use it for the part that you actually need. This is very important in terms of data querying, because in fact, this is one of the very few free lunches that we have in databases. Basically, if you can, for example, answer a request in, let's say, 10 hours with 10 machines, and now you say, okay, maybe I can do better than that, and with exactly the same computing power, let me use instead 100 machines, but just for an hour. What are my costs? It's the same costs. It's 100 machine hours. That's the same cost in dollars. But what's the difference for you as a user when you got your answer in just an hour instead of 10 hours? This is one of the very, very few free lunches that you will see in the area of databases. And this is thanks to the cloud. You wouldn't have that benefit if you were the only person in the world doing that. You only get that benefit because there's actually millions of people using and sharing the same servers, right? Okay. All right. Now I'm moving on to something that I promised earlier, because I said that we threw ACID overboard, at least in the early systems in big data. And we are replacing it with what is called the CAP theorem. So the CAP theorem is an impossibility triangle. Just tells you, you cannot have at the same time a system that provides partition tolerance and atomic consistency and what is the third one? It's like the Siebenbundesräte, I always forget one. So availability, the third one. So availability, atomic consistency, and partition tolerance. You have to pick 2 of the 3. You won't have the 3 of them. So what does that mean? Atomic consistency is all nodes see the same data. It's not the same as the consistency in ACID, right? It's a different kind of consistency. It means that imagine you have 1,000 computers, 1,000 nodes that provide S3 or whatever service to the public. People can connect to any of these nodes, right? They don't all connect to the same one. Atomic consistency means that no matter whom you ask, whichever node you ask and send your request to, you will get the same answer. This is atomic consistency. Why would you get different answers? Well, maybe you could get different versions of the file. Maybe there is a newer version on a file that you uploaded recently, and maybe not all the nodes have that newer version. So maybe some of the nodes will send you an earlier version and some others the newer one. But under atomic consistency, that won't happen. You will get that newer version from any node in the system. Atomic consistency. Second, availability. Availability is simple to understand. It's the idea that you connect to the system and you get an answer. Non-available is whenever you type the address of a website and you just get a blank page or an error or a 500 server error or whatever, right? So this is unavailable. Available is a guarantee that and this is with these 9s that I told you about. High availability means you connect and you get an answer, right? And the third one, partition tolerance, is the idea that your nodes might be all over the planet and you might have an earthquake, maybe in the middle of the Atlantic or Pacific Ocean, and suddenly some cables are cut and you lose the connection, right? If your system can nevertheless continue to work, if that happens, then this is called the partition tolerant system. It will even continue to work if there is a partition of the network into several parts that cannot communicate with each other. You cannot have the 3 at the same time. You have to give one up. Which one you give up, that depends on your system. They all make different choices. But here's the intuition, because it's a theorem, but we don't really have a proof. It's more like a conjecture or widely admitted principle, let's say. There is no formal proof. But what I can do is give you an intuition of the CAP theorem. And here's the intuition. Imagine you have your nodes. So these are the actual servers on your data center, right? That can answer your request. For example, that can be download the object with that object ID and that bucket ID, right? So consistency means I put all of them in green. They all have the latest data. And if you ask any one of these nodes here, you will get the same answer. Now, imagine that somebody, maybe it was you, connected to that node right there, where it's written update in red, and you upload a new version. So what's going to happen next, as you can imagine, is that this update is going to propagate in the system, right? It's going to be sent to the other nodes in order that they get the newer versions. This update, this propagation, can be synchronous or asynchronous. That also depends on the system. Synchronous means you need to wait until the propagation is done, and only then do you get the confirmation. Asynchronous means the system already says, yeah, whatever, I got your new version, and then it propagates in the background. And you're already gone by now. So this is asynchronous. So synchronous, asynchronous. But in any case, it propagates through the system. However, this is where the cable breaks in the middle of the ocean. Let's pretend that, I don't know, it's America on the left and it's the EU on the right, or Switzerland. It's not going to be available until the network is connected again. What do I mean with that? Imagine that somebody is in Europe and trying to access the nodes. They will only be able to access the 3 nodes on the right. What will they get? They will get the older version. There's no way they get the newer one. It cannot propagate anymore because that broke actually in the middle of a change. So what you have in that case is that you might say, okay, it's partition tolerant. It continues to work. But from the moment you said it's partition tolerant, you need to make a choice. There's 2 possibilities to go from here. Possibility 1 is I just switch off everything and I'm unavailable. Somebody connects there and asks for a file. No, unavailable. You just cut it. Of course, you're consistent, right? In that case, when it works, you're consistent. But when there is a partition, partition of the network, you just become unavailable. Solution 2 is you don't switch off the servers, you continue to work. However, the user needs to accept that they might get an older version. Then you do not have atomic consistency, right? So the first system that I described is called CP. It's atomically consistent and partition tolerant, but you're missing the A, right? The second system that I described, where you continue to answer with older versions, is called AP. You're available, you're partition tolerant, but you're not atomically consistent. And the third kind of system is AC, that's available and atomically consistent. But if there is an earthquake, you're done. This is all over. So you're not partition tolerant. So these are the 3 kinds of systems that you can have. It's a good exercise during the semester actually to ask yourself for every system, is it AC, is it AP, or is it CP? So this is the idea of the CAP theorem. There is a name actually for AP systems. AP systems that continue to serve requests even if it's older data. It's called eventual consistency. The system will be eventually consistent. What does it mean to be eventually consistent? There is, let's call it a misconception about eventual consistency that a lot of people understand it as at some point in time, the system will be consistent, meaning that all the nodes return the same thing. That's not what it means. It's actually a counterfactual reasoning. Is in the sense of that being eventually consistent means if, that's a big if no more requests arrive, no more upload requests, you don't change anything anymore, you don't upload new files, you stop writing to the system. So if you did that, if you stop doing updates and you wait for long enough, at some point, the system will be atomically consistent. What does it mean? It's just that all updates will have propagated by then. So there is a point in time at which all updates will propagate. In practice, though, it never happens that suddenly you don't get updates anymore. So this is why it's a counterfactual, it's hypothetical. If you would stop uploading stuff into the system, it would become consistent. But in real life, it never actually is consistent. So it's just that the updates propagate whenever you make them. All right? Any questions on the CAP theorem? Is it clear? The intuition of it? All right. So this is the CAP theorem, and a lot of big data systems work with the CAP theorem rather than ACID. But again, as I said, there are people working on bringing back ACID to big data, right? So there are people working on it. One last thing I want to say about the CAP theorem is that you will find papers or websites by big names, not going to cite any, that will claim to have solved the ultimate question on life, the universe, and everything, and finally built a CAP system, right? It's a very good marketing argument. We are CA and P. Do not believe them. Always read the details and figure out what there is in there that they are a bit tweaking in order to claim CAP. It's never the case. What happens very often when they claim to be CAP is what's really happening is that the probability of the network being partitioned is so small that it actually almost never happens. So of course, you're kind of optimistic when you say that, because that works until the day where the network actually breaks, right? But the entire marketing argument is based on the fact that if the probability is small, then you can pretend to be A and C. But on the day that there is a partition, you will have to make a choice between E and C, because you cannot have both. You can simply not have both. All right, so much for CAP. Let's move on to REST APIs. Who already heard of REST? Who never heard of REST? All right, some of you. So many of you. What about Zoom? Because we also have people on Zoom. Who on Zoom, can you raise your hand? Already heard of REST? R-E-S-T. You can raise your hand on Zoom, right? You can click. Right. I also see many people raising their hands here. Very nice. Okay. So very good. And for those who don't, then we will explain what this is. Okay. So whatever system or service or storage system or processing system, you need to use it, right? And the question is, how do you use it? Well, there's many ways. You can use it via a shell. On your good old command line, you just type commands and it works. You can also open a shell and type queries and it works. There is the fancier version of the shell, that's the Jupyter notebooks. We'll use them a lot in the lecture, and which are interactive notebooks where you can also put your queries, but it's a bit nicer than the terminal, right? Because you get all the nice plots and so on. Even though in the terminal you get with ASCII art, you can get beautiful things, right? But for most people, the Jupyter notebook are actually a good way. A third way of interacting with the system is by writing a program. Right? You can write a Java program or a Python program or an R program, and you just interact via some API with the system in order to control it. So it can be an API, it can be a driver via a driver, but if you have a driver, you will in any case have a programming interface, right? An API. Now, a fourth way that is very popular, and in fact, you will realize that many of the technologies that we will look at have a REST API. A REST API is actually, one way of putting that is that a REST API is the web done right, as the original intent was. So I'm pretty sure a lot of you know Sir Tim Berners-Lee. He's the founder of the web back then in Switzerland, right here in Geneva in 1989, I think. And he built a prototype of some hypertext-based protocol where you click on a link and then magically you land on another page. It sounds trivial today, right? But back then, that was actually a big thing, because he combined the idea of these hypertext systems with the idea of the internet and being accessible worldwide. And then you know what came next, right? In the past now, I have to say, 30 years. I'm not getting younger. 30 years, the web has developed massively, and the protocol is called HTTP, Hypertext Transfer Protocol. REST is actually just using HTTP, but natively. And I'm going to explain to you what that means. I'm saying natively, why? Because there's other ways of using HTTP as an additional layer. And one example of that is the SOAP protocol, where you just embed all your queries within some payload, but everything is a post request otherwise. But in REST API, it means representational state transfer. Everything is based on the native web, meaning you have a resource identified by a URI, Universal Resource Identifier, which looks like this. So I'm going to go quickly because, again, you're computer scientists, you're probably familiar, but just to set the terminology right. This here, HTTP, is the scheme because there's others. You can have FTP, S3, as we would see, is also a scheme. Then you have the authority, which starts with the // in that case, right? So //www.example.com. That domain basically is meant for use in lectures and examples because nobody actually put anything in there. It's basically for that. So www.example.com. Then you have here the path. So that starts with the / all the way here, right? So that's the path. Then you have with the question mark, the query. It's actually a key value pair model. You can have here, you have a key and a value, but you can pass many of them ampersand separated. And then you have the fragments. This is actually, you may have noticed that it jumps to some part of the page if you use it natively with a browser, right? But here's the thing, this is not necessarily something you type in your browser and get a page. This is a computer thing. So the web normally is humans communicating with computers. You type something on your browser and the computer answers with a page and pictures and so on. This is computer to computer, because the computer is actually programmatically creating that URI, shipping a request, getting an answer. So in the case of S3, this is what the URIs look like for a bucket on the top and for an object at the bottom. So you can see it's part of the domain. It's a subdomain where you put the name of the bucket. You see the region because it's actually region aware, can be in the EU, in the US, in Asia. And you have so the bucket only with just the domain, or with /object name, you can get an object. Note that there is also the S3 scheme that is used in some places as a shortcut for this, right? But it's just another kind of scheme. All right. Now, I should say one more thing about URIs. Actually, we shouldn't say URI. Everybody says URIs, but we shouldn't say URI. Do you know what we should say? Yes? IRI, exactly. That's what it should be called today. It changed a lot. There used to be URLs. Actually, we shouldn't say URL anymore. URL, URN, universal resource names, universal resource locators. Then it got unified as universal resource identifier. What is I for? Bonus question. International, exactly, because that was internationalized. So normally we should say IRI, but somehow there is so much inertia that everybody's still used to URI. So this is why everybody keeps saying URI. Right? So I also tend to say URI, I must admit, but that's just so you know. All right, this is for the resource. Then what you have is verbs. This is called the methods in HTTP. There's plenty of them. There's even extensions with more methods, but there's 4 that you must absolutely know. Get, post, put, delete. I will go through them. The idea of the protocol, you're computer scientists, so I know I won't scare you with that, but basically it's a server client thing. You send a request and you get an answer. In the request, you have a method and a URI, the resource, and you have a header and a body. This is optional. And then the response has a status code. You know them, right? 404, not found, and so on. A header possibly with some format information, and then the body, which could be an HTML page, a picture, and so on. What it looks like, actually, you don't see that because thankfully the browser is hiding that from us, even though you could go to developer mode and actually look if you're interested. This is how it looks like. You have this get on this with this host at HTTP 1.1, and then you get these headers and then the content of the page. So this is the HTTP protocol. REST works the same way, but the difference is that in REST, it doesn't have to be pictures and HTML pages and so on. It can be anything. It can be data, it can be, you can modify things, you can have some connected Internet of Things stuff on the other side and so on. So this is a generalized version basically of HTTP. What about these 4 methods I told you about? Get is technically getting, I would say shortly, getting a resource. You ask for a resource, but actually that's not correct. You don't ask for a resource. You ask for a textual representation of a resource. Because what you get is going to be text or JSON or XML or YAML or whatever. It's a representation of a resource. You can even change the format. So this is what get does. It's side effect free. You're not asking for any change anywhere. You just ask for something and get it. Right. Almost, because that excludes logging. You might still be logging the website, and in that case, of course, that happens something to the log, but it's not tied to the semantics of the website. So this is why we still say it's side effect free. If you program a REST API, never ever program a response to a GET method with side effects other than logging. Never. That's the semantics of REST. You cannot do that. Side effect free. Put means you upload something, for example, to object storage, and then you get an OK, it's been uploaded, right? So here it's you sending the data, and then the server says that it's OK. As you would expect, if you use put and then get, you should get back the same thing. Or maybe if you change the format in a different format, but the expectation is really that putting something, you can get it later. Under what I said on atomic consistency and all that, right? That you might not get the latest version if it's an AP system, right? So get and put, all right? Delete, it's very intuitive. You just say, okay, delete whatever is at this resource URI, so delete that resource. What you would expect is for get to send what error? 404, right? If you delete the resource and then try get, you should get a not found, right? This is the semantics. And finally, you have post. Post is a bit, I'm not going to say the garbage bin because that's not what it is, but basically it's whatever you cannot do with get, put, and delete usually goes to post, because post is super generic. You can have side effects, you can do whatever you want in there. It's basically the documentation of the API, of the REST API, that will tell you what it does. So this is basically where everything else goes, other than get, put, delete. There's other methods than that, but I'm not going to overcomplicate things. But probably now it's very intuitive to you that you can access Amazon S3 with a REST API, right? You can imagine if you use the URI of a bucket, you can create a bucket with put, you can delete it, you can get, meaning you list the content of a bucket with get. You can put an object by uploading a picture, you can delete an object, and you can get an object, right? And get, delete, put work as expected, right? It's very intuitive. You put something, you get it back, you delete it. If you try to get it, it's gone. Okay. Now, that was the REST API. Now I have one more thing to say. We said we simplified the system with a simple key value model. You have an ID, an object ID, together with a bucket ID that uniquely identifies an object worldwide. Is S3 a file system? The answer is kind of. Technically, it's not. It's a key value model, right? So it's object storage. It's a key value model. You upload and download objects tied with a specific ID. However, you can simulate a file system, because who says you can't have slashes in your keys? Of course, you can have slashes in your keys. So if you start putting slashes in your keys, these are still keys in the sense of this whole string, but S3 is kind enough that if you try to connect to the UI of S3 and so on, it's going to nicely interpret the slashes in that way. But again, it doesn't mean that it's hierarchical. It's a simulation based on the slashes that it's going to display it in that way. All right? One more thing you can do with S3 and similar systems is static website hosting. In fact, that's the cheapest way you can put a static website online. What do I mean with static? No PHP, no dynamic code. Just a static page, static pictures, and so on. JSONic, so we'll use that language. The web page is hosted on S3 as a static web page. That's an example. That's the cheapest you can get. So if you create a startup or whatever in the early stage and want a cheap way to host a static website, use object storage. It doesn't need to be Amazon. I'm not advertising for them. You have the same thing with plenty of other providers. It's all the equivalent services. But basically, it's super cheap because you don't have any code execution in there. All right? One more thing you can do is dataset hosting, because if you can put pictures and videos and static web pages and so on, you can also put data. Because that was actually a question during the break. What is an object? Well, for the purpose of object storage, it's just a sequence of bits. That's all it is. So the sequence of bits can be whatever bits you want to put in there. So the bits, as I said, can be pictures and pages and so on. They can also be data sets. In what format? I don't know and I don't care. Why? Because we're going to do that in a couple of weeks. For today, it's any format, anything, any sequence of bits that we put there. We'll worry later about what they actually look like and the formats and the syntax and so on. So it can be absolutely anything. But as you will notice, the data sets are very often in the form of plenty of files in the same directory, because it's just distributed over many files. That was also another question that one of you asked. I'm coming to you. That's another question somebody asked. How do we store petabyte data sets if there is a limit of 5 terabytes? Well, the answer is you just use multiple objects, multiple files. Yes, go ahead. Maybe the catch box, that's what it's for. Oh.
So I was going to ask, I know Amazon has also the Dynamo storage, which is again a key value store. Is the difference between Dynamo and S3 in terms of the actual size of files, or is it also the sort of consistency and availability they provide?
So it's an excellent question, and I'm not saying it's an excellent question in order not to answer it. It's just because we are going to, in fact, talk about DynamoDB as well. I don't know if I'll start today, but tomorrow in any case, and I'm going to explain the differences between the two. Your guess is correct. It has to be with the size of the objects that you put in there. Another example is the latency. As we will see, it's not the same latency guarantee, right? But that's a great question, and we'll come back to that, right? The catch box, maybe?
Isn't also DynamoDB a relational database storage thing? Whereas S3 is just object storage.
So if you mean in terms of terminology, relational, we often mean relational database management system, right? In that sense, DynamoDB is not a relational management system because it doesn't offer SQL and high-level data modeling at the scale of tables and so on. A key value store, just like an object store, is a low-level physical storage technology, right? It's a very primitive technology that just uploads and downloads things from the system. That's all it does. And in the fact, there was a hype around key value stores. I think by now it's probably a bit over, but 10 years ago, everybody was using key value stores everywhere. But the danger is that many people were using key value stores while they should, in fact, have used the relational database management system instead, like PostgreSQL, for example. So right now, I think it's no longer key value stores, it's probably the blockchain. So now everybody has a blockchain and is doing something blockchain related and so on. And interestingly, the same thing is happening with blockchains. A lot of people are using blockchains while what they really, really, really need for the use case is a relational database management system. Right. So what's important to understand, to come back to your question, is that a key value store like DynamoDB is not a relational database management system. You can build a relational database management system on top of it, but it's just a low-level component that would be at the bottom of the stack, right? Does it satisfy you as an answer? All right, awesome. Any other questions? Anybody? All right, so let's continue. How much time do I still have? We'll have a bit of time. All right. Somebody mentioned Glacier actually during the break, which is a good point. So actually, there are several ways you can use object storage. And actually, if you want to save costs, because some people use that kind of storage for backup. So if you back things up, who cares if you get an answer in 100 milliseconds? You don't need that. You can wait for a couple of hours in order to get your backup back, right? Because a backup, you're already happy enough that you're getting your data back, right? So for this reason, you can save on costs and pay less in exchange for a higher latency, meaning that you won't have these 100 milliseconds, you might have hours to get. Now you're gonna ask me, why hours? Well, hours are because you typically store that kind of data on magnetic tapes in some specific storage center. And at that place, what you have is little robots that go all over the place and go get the tapes and so on. So you need to wait for the robot to get there, fetch the tape, bring it back, put it in the machine, read it, and so on and so on, right? So this is why it takes time. But magnetic tape, you would think it doesn't exist anymore. Yes, it does. We even have some at ETH for the backups of your directories. It is super cheap. That's the advantage. I think one question during the break about tapes is how you scale or store the files. Well, you will not use Glacier or magnetic tapes to actually query your data. That's not how you do it. You would first copy over or restore your backup into a different system like the normal latency S3 or Azure blob storage or HDFS that we will see next week and so on. And then you go ahead and query your data, right? So this is really just for backup that you pay less and you accept the hours it takes to get it back. All right. Now I need to prove to you that I'm not advertising for Amazon because there's plenty of other providers, but actually they work more or less the same, right? So Azure is the one we use during the lecture. Why don't I start with Azure? Just because it has more bells and whistles than S3, right? So I wanted to start with something simple. Now I will compare and tell you what Azure Blob Storage is. So it's basically the same thing, but in Azure. All right, so here I'm directly throwing the differences at you, but you will see it's pretty simple. What about the API, right? So what is an ID? What identifies uniquely an object? We saw in S3, you need a bucket ID and an object ID, right? That uniquely identifies worldwide any object. In Azure, they have three parts. This is your account. This is your account ID. This is a container. So what's the difference? Now you can have the same container name as somebody else because with your account ID, you disambiguate anyway. So that's the reason, right? So your account, a container within your own namespace, and then what's called the blob. Blob is for binary large objects. It's also a term used in relational databases when you want to store large binary values in a relational table. So Azure Blob Storage. That's the first difference, but is it really a difference? Not really, right? That's the same idea, right? You identify an object or a blob, they just call it a blob. O is for object anyway, so that's really the same. And account plus container is the same as the bucket, right? Okay, now what about the object API? Well, S3, that's something I haven't told you yet, but if you want to upload a very large file that's 5 terabytes, you are allowed to upload it in several subparts. Right? You don't have to upload in a single upload, right? So you can actually, in the API, you are able to say, I'm uploading parts 1, 2, 3, 4, 5, and at the end you say, okay, now put together 1, 2, 3, 4, 5, this is my object. That's what the API allows you to do. In Azure, they provide 3 kinds of blob storage units. Block blobs, this one is hard to say, block blobs, append blobs, and page blobs. Block blobs are the ones equivalent to S3 mostly. These are the ones where you upload your pictures and data sets and so on and so on. But why do we have the other two? Append blobs are for logging. If you keep a journal and keep logging and logging and logging, it's just optimized for appending, right? Pages, this is for virtual disks. If you store data for the virtual machines, these are used for the disk data. But again, the most important for us is the block blob. You see the maximal size, 190 terabytes. This is much more than the 5 terabytes in there. Append, 195 gigabytes. This is less, and 8 terabytes for a page blob. So these are the limits. Actually, they even give you details in a way that Amazon doesn't, because we don't know much about how S3 is implemented. Sadly, there is no paper or anything. We just know from outside. But for Azure, there is a paper, and they tell you the size here actually corresponds to 50,000 blocks. Each block can be at most 4 gigabytes. This is how this is computed. All right, so what is inside Azure? Well, they group the racks. You already know what a rack is now in the data center. Well, now you have plenty of racks together, right? So 10 or 20 racks, that's a lot of machines. Basically, with each rack containing 18 storage nodes, that gives you 30 petabytes for what they call a storage stamp. This is the name of these 20 racks, right here. It's a storage stamp. One storage stamp can store 30 petabytes of data. They don't have just one of these. They have plenty of them all over the planet, right? But they basically work by increments of 30 petabytes. They also try to keep it below 80%, right? 70, 80%, to always have an available space. What happens if you are above that and 90%, they will just open new storage stamps and rebalance a little bit the data to other stamps, right? But they always try to keep some capacity. You don't want an error that the disk is full. That doesn't look very serious when you offer cloud storage, right? So this is the idea. Another thing they do, and we'll come back to that plenty of time, is that they replicate your data. This is how you offer this 99.9999999% of loss guarantee. This is a storage stamp with the 3 layers to find the account and the container and the blob. So it actually propagates down there. Within the same storage stamp, meaning there, here, there's already replication happening. The replication happens synchronously. Do you remember what that means? It means when you upload something, you are blocked. You need to wait until this is duplicated within the same storage stamp. When you get your OK, it has already been replicated within that stamp. But once this is done, it will again replicate, but this time after confirming, to another storage stamp. This is why it's called asynchronous, and it will also ship over your data to somewhere else. This is in the case there is a fire or an earthquake right there. This happens. It actually was in the news a few years ago that a data center burnt, I think in Eastern France. Sadly, they didn't do any backup. You can imagine the consequences in terms of, it basically kills your business, something like that. So this is why it's super important to be protected and to have it at several places, just in case something happens. For this reason, you will make sure to distribute things all over the planet. Well, I'm not talking about legal requirements or data protection just yet, to make that point. If you have your data all over the planet, that gives you two advantages. Two. The first advantage is that if your customers are all over the planet, you will serve the data to them, the pictures, the videos, if you're a streaming service, for example, you will optimize the latency. If somebody is in the EU, you'll just transmit from Frankfurt. If somebody is in the US, maybe from your data center in Illinois, right? In Asia, maybe from Beijing. So this is how it works, right? You optimize your latency. Do not underestimate the speed of light. Because yes, it's instant over the Earth, but compute the time it takes to get, let's say, from America to here. That's actually already dozens of milliseconds, above 100 milliseconds. And to add on top of that, that it doesn't propagate in a straight line yet. Now with satellite constellations, it might, but for now, it actually goes all over the place. So asking for data coming from the US, you get some latency. If you ask 100 times for it, you're going to notice. Just once, maybe not, 100 times you will. So this is why being close is actually very important. Second, you're resilient to natural catastrophes because if there is an earthquake somewhere, you still have a copy of your data elsewhere. Now, of course, you need to add considerations of data protection, right? Because also for legal reasons, you might not be allowed. If you're a bank, for example, you might not be allowed to have a copy of your data somewhere else, right? But you can still spread all over the country, right? For example, if you're a bank, you probably want to have your data in Geneva, in Basel, in Zurich, in St. Gallen, you know, and be safe. All right. Which brings us to the question that you asked earlier about key value storage and DynamoDB, which we will do tomorrow, right? So I'm going to finish today with just a question that I will ask almost at the end of every one of my lectures. I just hope it's still there. Just wait before you go for that. So this is basically your opportunity to accelerate me or to slow me down. So how much of today's lecture did you understand in the lecture hall and on Zoom? Everything, more than 80%, 50% to 79%, or less than half. This is my way every week to see where we are, if you're following what I'm saying or not, and then I can adapt, right? If I see that nobody understood anything, I will re-explain in the next lecture. If I see that everybody got everything, then I can maybe accelerate a bit because you're bored and so on. What you see here is a typical, that's kind of my target, right? I try to target for a majority in 80% to 99%, which is the sweet spot, right? So this looks good. So we'll just continue tomorrow in the same way. Thank you very much. See you tomorrow at 9 a.m. in the main building.